everybody to the first afternoon session. We're going to have 3 exciting papers in the session. My name is Matthias Niessner. I'm a professor at TU Munich, and I have the honor to chair the session. We're going to start with the first paper, Compact Landmark Layouts for Performance Capture, and it's authored by Eduard Zell and Rachel McDonnell, and Eduard will give the talk.
Thank you very much. So in the following, I will present a new method for computing facial landmark layouts that are compact, fast to compute, and semantically plausible. So why should we care about facial landmarks at all? In the past, facial landmarks have been widely used for motion capturing, but they remain even today under the hood of many markerless tracking technology. So be it in annotated image data sets for facial tracking. So the landmark layouts are there, but we just do not see them in the first place. Over the last 25 years, a number of facial landmark layouts have been proposed. Interestingly, nearly all layouts have been derived purely empirically. And apparently the main reason for the frequent use of the multiply layout is actually the huge number of annotated images. Why did previous work and methods had so little impact on landmark layouts in practice? We believe that this is because of the following reasons. First, the computed layouts lack a semantical basis, and landmarks appear to be a bit random, so placing them in practice is challenging. Second, previous methods solve for optimal placement. The actual number of landmarks remains a user input variable. So whether placing 20, 40, or 60 landmarks is unknown. So what differentiates actually a good from a bad layout? Typically, the more landmarks we have, the smaller will be the reconstruction error. At the same time, having less landmarks can substantially speed up and simplify tasks, like data annotations or computations in general. However, if we use too few landmarks, we might not be able to recover the facial motions anymore. Thus, similar to all compressions algorithms, our goal is actually to find an optimal Pareto solution. So what we are looking for is a balance between a small reconstruction error and a small set of landmarks. In the context of compact landmarks, the facial animation pipeline has strong resemblance with general lossy data compression. We start with the dense motion, add a compression step to sparsify the sequence, and hopefully we can recover the full facial motion afterwards. Previous work varied not only by the suggested methods, but also with regards to the assumptions they made to the input. Cohen et al. Assumed that dense motion is given, and the model for facial animation is not known. In the first step, they reduced a dense sequence using PCA, and then clustered it using k-nearest neighborhood. The drawbacks are that a large sequence of dense animation is required. So later, Reverdy et al. Suggested to cluster only the blend-shaped matrix as it is, without making any assumptions on the input motions. So here they take advantage of the limited representation power of the facial animation model. However, the problem here is k-nearest neighborhood is known to be unreliable for high-dimensional vectors. Different to that, Lee et al. Suggested an end-to-end optimization method that is based on surface deformation. Unfortunately, their method is prone to local minima and by design not well compatible with shape-based animation models. Since this method is will be prone to local minima, we also compared to the least square measures by Sorkin and Mark Alexa, which is highly similar to the method of Lee et al., but computes a global minima. Finally, in the context of inverse kinematics, improving the condition number have been suggested. When solving the inverse problem of blend shapes, we must look at the delta blend shape matrix. Unfortunately, the condition number is pretty much constant, independent of the vertex set. So this solution does not work for blend shapes. In our method, we suggest to derive landmark layouts from blend shape models. First, blend shapes are probably the most popular method for facial animation. Blend shapes can also serve as a good proxy for nonlinear shape-based methods. Furthermore, the animation model must be created anyway. We must have the blend shape models to animate them. In contrast to that, capturing dense motion sequences to compute a sparse layout leads to substantial overhead. And last, we take advantage of the embedded semantical information in the, so this is the facial range of motion and the semantical decomposition within the blend shapes. In our approach, we assume that at least one representative landmark is required for each blend shape. To quantify the quality of each vertex, to represent a blend shape, we introduce a weighting function dependent on 3 variables that I will discuss now. First, we consider the relative blend shape displacement. We preferred the relative metric over an absolute to balance better between large expressions, like mouth opening, and more subtle, but still very important expressions, like an eye blink. Second, and different to all previous work, we add a visibility weight. In the simple case, this is a check for self-intersection between the camera and each vertex. In the case, if the camera position is unknown, which is most likely the case, this generalized to computing the ambient occlusion map, which is equivalent to sampling the hemisphere of every vertex for self-occlusion. We take further advantage of the fact that blend shapes cover roughly the expression space and compute the visibility weight based on all ambient occlusion maps. The last ingredient to quantify the quality of each blend shape, or of each landmark, is to discard vertices with small displacements. This establishes a lower bound to the signal-to-noise ratio. So the higher the cutoff values, the lower will be the reconstruction error in general. However, setting the cutoff value too high will quickly oppose our goal of having compact layouts. So, having computed the quality of each vertex to represent each blend shape, we are ready to compute the layout itself. To do so, we use, a variation of the set-cover algorithm. Our goal is to minimize the number of landmarks. The variable fn is basically a switch whether a vertex is a landmark or not. To consider the quality, we use a weighted set cover variation. And finally, we add the inequality condition that the landmark must exist for every blend shape. Integer optimization, which we have here Boolean optimization, in fact, but the general problem is integer optimization, is known to be slow. However, we obtained a global solution in all our experiments using Cplex in less than a second. And with this speed up, we are among the fastest methods that exist. So this is the result if we apply uniform weights. It will lead to sparse but implausible results. Taking displacement only, landmarks are placed in areas which are difficult to capture. If we go for visibility only, landmarks are easy to capture, but we lose our semantical plausibility a bit. And the best results are actually obtained by combining the two metrics, and we can push it further by adding a symmetry constraint. Different to previous work, we do not prescribe the number of landmarks. By setting the cutoff value, the user controls indirectly the number of landmarks. So we start here with 0.1, and little by little increase the value, so you can see the impact. Please notice that the layouts remain nearly symmetrical, although in this case, we did not enforce symmetry. So this is the result when we start to enforce symmetry. The similarity is given to the previous one. So a few more results. We computed landmarks for different line shape models, like the Apex metahuman characters, consisting of 160 blend shapes roughly. iSquare's visual effects model, but also cartoony models. Please notice that the layouts are, in most cases, or in all cases, remain the semantic plausibility. And what I find most surprising is roughly 30 to 40 landmarks are sufficient. So sometimes you want to go for more than one marker. For example, to be more robust on occlusion. So how can we extend if we want to add, to ensure that one landmark is given for each blend shape? One natural extension would be to go for a dual cover problem. So the only difference here is this 2 marked in red. The problem is, while we get a result, the result is not necessarily better. So most landmarks are clustered. Instead, we suggest an adaptive multi-cover algorithm, which is iteratively. In the first step, we solve the single set cover problem as discussed previously. Then, we discard selected landmarks and nearby vertices. Furthermore, we discard sufficiently covered blend shapes. And then the process is repeated. The advantage of this approach is, first, it's easy to extend. And we can add any heuristics that we can think of into the discarding process. So this is kind of like really easy to adapt, and from all the experiments we did, this turned out to created the best results. So to compare with previous work and to make the comparisons fair, we assumed that the blend shapes and the dense motion sequence are the same here. And we only considered displacement here. No explicit symmetry and no visibility constraints have been considered at this comparison. So this is our result. This is the result from Cohen et al., Reverdy et al., and Sorkin et al., which is kind of like a variation of the method of Lee et al. Notice the outliers for the methods of Cohen and Reverdy. And this is the layouts generated by the method of Lee et al., where we use the previous methods as initialization. And notice that the method is very prone to local minima. So there's a high similarity between the initial layout and the final layout. So in our case, we maintain a nearly symmetrical layout without having symmetry constraints, we barely have layouts, and we are among the fastest. We also provide ground truth comparisons with the 4D sequence. First, we compute different layouts for blend shape models with a character derived from Epic's MetaHuman. Second, we create a person-specific blend shape model for the 4D dataset of Zhang et al. Using deformation transfer. Last, we fit the person-specific blend shape model to the 4D data under the consideration of each vertex. So we have the full vertices to create the ground truth data. Having now a 4D sequences in correspondence with the blend shape model, we can test the reconstruction quality of the different results. And here we have also the lowest numerical error. Looking at the reconstruction error of the entire sequence, the difference is sometimes quite small, and in other cases, the error is bigger. And when we do synthetic ground truth comparisons, where we randomly activate different blend shapes, and then try to fit to this animation sequence, it confirms that the assumption we need at least one landmark per blend shape is valid. So if this is not given, this is actually the expression where the reconstruction error is biggest. We also compare our layouts to different empirical layouts and observe that our layouts are substantially more compact. So if we plot it, we have among the smallest set of landmarks, but at the same time we ensure that our landmarks cover all blend shapes. This is typically only the case for layouts that have twice or 3 times as many landmarks. And the reconstruction results are here more or less the same. So we are on par with layouts that have twice as many landmarks. Here, to make it a little bit easier. So this is the visual result, and the numerical result is also the same. So finally, we also compare animation reconstruction under real conditions. Here we have all kinds of difficulties like different characters, inaccuracies in landmark placement, etc. Nevertheless, the animation reconstruction is again on par despite using only half of the landmarks. Our method creates rig-specific layouts. However, in our experiments, we observe a recurring pattern. That's not surprising because most blend shapes models are based on the facts. So let's try to derive a layout based on facts. First, we compute different layouts using our minimum displacement threshold based on the 3D facts dataset. The layout is reasonable, but based on our experiments with all kinds of layouts, reconstructions, etc., we would anticipate issues in 2 areas, which are the eyebrows and the lips. Thus, our idealized layout would look more like that. Comparing the multiply layout to ours, we see a sparse sampling of the brows, eyelids, lips, and chin. The landmark location around the nose differs substantially, and in contrast to our model, no landmarks exist around the cheeks. It is also worth mentioning that landmarks are barely placed at the temples, the nose rim, and the corners of the eyes. These areas seem to be more suitable to compute the rigid motion of the head. And in fact, they've been mentioned already previously by Bieler et al. So to conclude, we presented a new method for computing compact facial landmark layouts that is fast and I would say quite easy to implement. It has good reconstruction results. It's suitable for different types of plane shape models, be it cartoony, with high-end visual effects, or real-time, and that has high semantical correlation with empirical methods. Thank you very much.
Cool. Thank you very much. I think we have time for questions. Maybe I can start with a question. So I'm actually quite curious like we do a lot of stuff on computer vision where we detect landmarks within images, right? Mm-hmm. So there's two parts of it. One part is if you have an existing landmark model, how complicated would it be to move it to a new landmark model? And could you use existing detection methods such as OpenPose or so to kind of retrain it with existing data? Is that possible?
I think it's possible. It was already done. So I would need to look up in the paper for the exact reference, but basically, just go to the slide, to the correct slide. No, sorry. It's very at the beginning. Can we go to slide 3? Can you press 3? Okay, anyway, so I've showed maybe this one. So the graph where all the different layouts are there. So this is largely inspired from a paper where they tried to uniform all the different annotations and to map it into the multiply data set. So, and retraining I think is possible, especially if you combine it, so landmark estimation methods with where you fit afterwards on pixel level the accuracies. I think the current methods are accurate enough, and then you should be able to refit to any layout that's there.
How difficult do you, how much do you think it matters in terms of the detection performance with respect to the respective landmark model? Right, because the argument what you're making is like, oh, let's use the best landmark model that approximates the plane shape motion as best as you can. Now the question is, if you're dealing with like a mocap suit or something like this, you have physical constraints where to put the markers on and you want to detect them and have a certain coverage. So I would assume that this is quite important in the design choice too, right?
So what we figured out is basically that most landmarks that we suggest for the dynamic capturing, once again, so this is only the dynamic capturing, not the rigid position of the face, are from the semantical point of view easy to annotate. They're sometimes easier to annotate than an existing model. So for example, the Chen is is highly perspective dependent. So they are, with this regards, easier to annotate. And what the difference is also, especially in the multiply method, we have many landmarks that characterize more static parts of the face. So the entire nose, for example, characterizes more the static part. So I could imagine, and this is an assumption, that capturing the nose with an existing layout model is extremely difficult because the landmarks are not just in the right position. Same for the cheeks. For the cheeks, actually there's I think a Ziggraph publication from Cow 2013, markerless capturing in real time, where they claim to add some markers at the cheek, and this improved their model substantially. I think this was never used again by any methods follow-up, so apparently it makes sense.
Cool. Thanks a lot. Any other questions? So I have one more question. In terms of the evaluation metrics, could you imagine like some perceptual metrics there as well, where it would kind of like figure out the quality, how humans kind of perceive the respective motion. Is it something you looked into?
Yes, we have actually one diagram in the paper. The reason why I didn't add it into the presentation is from the reviews we know that reviewers were always looking for squared mean root error. So there are perceptual evaluations, and they are basically looking at how much does the curvature change. So if you have a constant offset of the cheek, let's say, that's fine. But if you create some wrinkles, this is typically like a perceptual error that's easy to spot.
I mean, are there some user studies or so where like
yes,
you could, I mean, this is probably pretty difficult to do, right? Because you have to say, oh, does this face look more realistic, quote unquote, or does it get the expression better across?
No, there are actually user studies on compression for meshes, and the visual compressions versus, or visual artifacts versus numerical artifacts. And yeah, so there are also metrics derived, so you can in advance estimate with the correlation index, I think up to 80% or 90% on the mesh level, not texture level, whether this is an artifact or not, and how much is this considered as an artifact.
Cool, thanks. Any questions from the audience?
So thank you for the presentation. And I have a question about slide page 34, which might be a little bit out of scope of your work, but I'm just curious, a little bit curious by watching the video that you show. I have the impression that although all these markers have been put on the face, the tracked eye gaze, well, the position of the eye rotation is somehow not as realistic as what you can see on the person itself. So do you think it's possible to realize high precision eye gaze tracking through this kind of setup, or do you have any comments on this eye tracking stuff?
Okay, so comment number one, the eye motion itself in this video was generated procedurally, so we did not capture the eye motion here. So the eye motion is just generated procedurally based on the eyelids. It's kind of like, yeah, derived from it. Thus, it's not 100% matching. So if you are looking for eye capturing, I think capturing the iris and basically the rotation of the eye seems to be quite effective if you want to capture the entire face. So yeah, I think it's kind of like there is a high standard reach. We just didn't capture it because we didn't want it to have a head-mounted capturing device in this case.
Thanks a lot. Again, let's thank Eduard again for the great talk. We're moving to the next paper in the session. So I think this one is remote now, right? Okay, so the paper is Cast, Character Labeling and Animation Using Self-Supervision by Tracking. The paper is authored by Oron, Zell, Rapoport, Ariel, Shamir, and Oron will give the talk.
Hi everyone, my name is Oron, and I'm a PhD student at the Reichman University under the supervision of Professor Ariel Shamir. Today, I'll be giving a talk about our work on animated character representation in a style-aware method using self-supervision by multi-object tracking. So computer vision, classic. Computer vision state-of-the-art algorithms are applied today to many tasks like detection, segmentation, and identification, and others. However, these methods work perfectly mainly on photorealistic footage, like on my kid's picture here. For example, let's take multi-object tracking, which is a well-studied field, and BiTrack, which is a state-of-the-art multi-object tracker. This amazing work captures all pedestrians in the street in CCTV footage. But when we apply it on animation, this model captures only several of the animated human characters and none of the tractors or non-human characters. Same happens when we apply it on some more abstract styles where none of the human characters was captured here. So what makes the difference? First and foremost, animation is produced totally differently than photorealistic footage, as you know. And the large variation in styles makes quite a factor that essentially appears totally differently in the data. Like when we apply it on stop motion, manga, cutout, the variance between anthropomorphized characters is high due to style, shape, and animation techniques. On top of that, a character can wear any shape of a non-human character, as we saw before. And lastly, the large variation of a single character could be quite significant, as characters or animation do not apply with physics laws. This is Cosmo, a fairly simple character with just a few colors and a distinctive pattern. In the following video, Cosmo changes about 30 shapes in just a matter of seconds, from a fish into a jackhammer, and so on. So we're looking for a method to represent characters while a character could wear any shape, like in this ridiculous example. We'll look for a solution to take a full video and generate a semantic embedding that is suitable for this specific style. One way we can go is to train a universal model that can work and generalize across any animation style. However, we suggest to go differently, to use a pipeline to learn a representation for a specific style as we found it to be optimal. We use shot segmentation on the video in order to find the exact frame in which each shot was changed. We sample frames and apply an object detector that was trained to detect characters. We use a simple method that uses a single class or two classes, a character and a non-character, on which we apply a multi-object tracker per scene, meaning, or per shot, meaning that we can tell the bounding boxes belong to the same character per specific shot. We later sample triplets and apply contrastive learning in order to refine the network or the representation towards this specific style, which we dive into shortly. So some implementation details. Shot segmentation is based on color histogram change monitoring with a fairly simple method that works pretty well on our data. We find the exact frame in which a shot was changed. For detector, we use YOLO V2, which was found to be fairly cheap in terms of computation, and we fine-tune its person detector class on top of our training set, which includes 61 different styles of animation. We apply it in the wild, meaning that we do not train it from this point on, and we fit it to be recall-oriented, meaning that we won't get almost false negatives. For multi-object tracking, we've been using a classic max-flow min-cost method by Zhang et al. And improved its transition cost estimation, meaning that matching between consecutive frames of different candidates, being the bounding boxes detected, are matched better with our method, where you can find more details on the paper. For embedding backbone, we use SERESNext, which was tuned over the same training data set. We leverage the ideas of triplet loss, which is one sort of contrastive learning, where the method essentially takes 3 examples as an input and penalizes the network for placing the anchor. Okay, so we have an anchor, a negative and positive example, where the anchor and positive example share identity, for instance, and the negative has a different identity, where we want to have a latent semantic embedding which places some information or encodes some information with respect to the identity in the latent semantic space. It does so by penalizing on cases where the anchor is closer to the negative example than the positive with some margin alpha. The main idea of our paper is that by taking a single shot and considering its tracklets over time, we can sample a frame with at least 2 bounding boxes having 2 characters, essentially distinct in the spatio domain, where we can consider them as an anchor and negative examples. We can then sample a positive example from the anchor's tracklet, having a triplet which we can leverage in order to fine-tune the representation towards this specific style. Most of the triplets look like this example, where the anchor and positive share identity, and we can see the pose variation where the network will leverage to encode their identity and be agnostic to pose variations. Some examples are actually non-trivial, like when Cosmo changes shape. What happens, sorry I was not in sync, but what happens when the multi-object tracker fails? Like these 2 purple examples actually does have a different identity. Yet they were sampled as a valid triplet while they're not. Or when the detector fails, meaning we have a non-character detected as a character here below. We believe that such examples, although do not encode identity properly, may still teach the network to fine-tune the network towards the style and texture in this specific animation. Before you can see image clouds of our representation, or the first two principal components of our representation, which has a 2048 dimensional size, before and after self-supervision. One can see that our representation encodes the identity of these 3 characters much better after self-supervision. Some results, but before that, we'll see 2 components that we used in the applications. So first, we have compiled an evaluation data set that includes 7 series with 2 episodes per style, meaning a training episode and a test episode, with a total of 49 different characters altogether. Another component that we use in our applications is a clustering algorithm, where the clustering algorithm that worked best for us is dbScan, which is a non-parametric clustering algorithm that does not require the true number of characters in the video, in our case. And on top of that, usually videos tend to have a starring character and long-tail characters, where the star gets much higher frequency over different frames, and you have some characters that appear only for a few shots, for instance. So this algorithm works well on such a data, and we find it good. Also, this algorithm disregards noise. So if we have considered the detector in our pipeline earlier as recall-oriented, you may say that this component is kind of precision-oriented. Our ablation study shows that self-supervision generates significantly less clusters of more characters, where 90% of the clusters are totally pure. So, for instance, an average episode, a test episode, unseen episode, has 20 different clusters, where it actually has 13 characters depicted in those. And we should expect that 2 can be messy and 18 could be further leveraged as they are totally pure. So we use that later in applications. The first application is dictionary building, meaning we take a video and we unsupervisedly get the complete cast of characters in this video. This unsupervised method requires clustering, filtering of insignificant examples, and assigns essentially a cluster per character. For example, the movie Cars 2 was part of the test set of Zell AMCD, which a data set which was presented by Somandepalli et al. In 2018. We can see here some characters that look very similar but have different identity. And the algorithm managed to cluster them separately, which is great. And we can see a bad example where this red car, Lightning McQueen, which is the star of the video with the highest frequency, was over-segmented, which is less optimal. Another example is from our own evaluation data set from the series Southpark. You can see that it captured all the main characters, including the supporting characters, the long-tail characters that appeared throughout this test episode. You can see one example of false positive of a non-character. So Somandepalli et al. Have suggested the dictionary building task. We have compared our work, and our method has outperformed the results on their test data set with respect to all metrics, introducing much higher cluster purity of 95% and less exemplars per character. Our second application uses the previous step and a human in the loop here in order to name those clusters to be used as training set to build image classifiers to name those characters automatically in other frames. And we leveraged this method and applied it on the test episode. The following statistics were evaluated on our evaluation data set, where it yielded about 89% F1 score by only labeling the clusters. The third and last application further applies this method on all frames of the video, yielding a full labeling. Here we apply the image classifier trained based on our method on the training episode over the test episode, frame by frame without temporal coherency, which is left for future work. You can see that although it is a bit jittery since it is applied frame by frame, it still has some robustness and captures these aliens, which was not part of the initial training set. This approach empowers media companies to estimate the screen time per character. This opens the door for gender bias estimation in animation, which would be very costly to do manually. For instance, we found that on the video Cars 2, only 22% of the screen time was by female characters, which is not enough. One interesting point that we've discovered is what makes the difference between a background object and a foreground character, at least from the detector's perspective. And we found it to be hands, feet, and facial attributes. And there were, of course, learned implicitly by the network. The following confusion metrics showed that the results over the series Fireman Sam were actually had over 80% of the error caused by only 4 out of the 14 characters. The reason is, of course, that the 4 firefighters over there are all wearing the same uniform, which undermines the selection of a full body detection by us as the unit of analysis of the detector. Another limitation is related with the fact that we worked with a pre-trained both detector and a base embedding, which requires some animation data to be trained upon. We also, although we trained the detector for recall orientation, meaning that we don't want to miss any character, we still could not recover cases where we failed to detect one. And lastly, as mentioned before, we can further use the temporal information for smoothing and analysis. So to summarize, I presented our method for representation learning of animated characters using self-supervision by tracking. And 3 different applications. The first was the dictionary building, which was an unsupervised task. Another with the human in the loop that leveraged this method in order to label a training set and build image classifiers. And finally, to apply it on the full video frame by frame to estimate the gender bias. And with that, I'll be happy to answer some questions.
Cool, yeah, thanks a lot. We have time for questions.
Hi, thanks for the presentation. It was a really nice work.
Thank you.
So I have a question on how you handle style. In this case, now you showed demos where you had CG characters, you had South Park style characters, or whatever. So how did you handle training? Did you do some data augmentation? Did you do some kind of normalization or not?
So thanks for the question. We, as mentioned before, try to learn a representation for a specific style. So we fine-tune a baseline embeddings using our method, which analyzes the shots, applies detector and multi-object tracking to sample. All of this work was done to sample triplets. Those are used in order to take the base embeddings and fine-tune it towards this specific style, for instance, South Park or Cars or whatever, which are different as they use different techniques, etc. The idea behind it is that by tracking those characters over time, we can build those triplets with respect to their identity. So we were kind of doing 2 tasks at the same time. We both learn the style and learn to be invariant to pose and dressing and and shape changes, as we saw in this Cosmo example. So the bottom line is we generate a network for each style.
And what about the loss? Does it consider like some perceptual metrics?
So triplet loss uses the basic hypothesis that can I get back to it? Here. So we analyze a single shot in every time, as we can't match between shots, right? Because character can appear elsewhere on the frame. It could be a different scene, etc. And running detection and multi-object tracking, we sample those triplets, okay? And the triplet loss essentially encodes them towards the latent semantic space, which by taking the assumption that the multi-object tracker works well, and the fact that two distinct bounding boxes of the detector within the same frame have different identity, then we can assume that by using the triplet loss, we kind of encoding the identities of the different characters without even knowing their name or identity, right? We simply know that since we've taken those two examples from the same frame, they have different identity, and since we assume that the multi-object tracker works well, then we can assume it has the same, we can sample from the anchor's tracklet another example to be considered as a positive example.
Okay, thank you.
Thank you.
Great work.
Could I ask a question, please? Over here. So I'm going to abuse my authority over the mic and ask one question. Thank you for the presentation. I'm interested and excited about applications. To verify my understanding, so you are using object tracking to create the triples which are used for the training later on. It seems like you have, during each of the frame, you have to know the identity of each character. So here we can see green and red box per each frame. And on this, let's say it's green and red on the first, and then the second one it is accidentally swapped. Does that ever happen, or is that handled by the tracking well enough?
So it kind of depends on the algorithm, the tracking algorithm. I can say that by looking on the data, really the most of the examples are basic like this, and it works well. And we can find some crazy examples, as mentioned before. And I've tried to bring two examples of two failures which could found in the data, like when the multi-object tracker fails. But that's not a bad failure. Like a bad failure would be to give a negative example which has the same identity as the anchor, and a positive example which is a different identity, right? This is the worst case that can happen. I did not see it in our data, but what I did see is this example where these two purple characters actually stands next to each other. You can see the anchor point there. So it basically stands next to each other. That's why the multi-object tracker was failing, because they have generally the same color and shape, and they positioned similarly on the frame. But and we also saw an example where the detector fails with a false. That's not a character, right? So we think that although these cases do not encode the identity properly, it may still fit the network towards this specific style, like the texture, are genuine from the data itself, and it kind of learns still the textures and style without knowing the identities, but it's not a foolproof, right? And these cases are just a few, so.
Great, I see, thank you.
Sure, thank you.
Questions? Here in the front.
Thank you very much. I have a question with regards to character design. So cartoony characters are designed typically like to stand out and to differentiate a lot. So there's the silhouette, which should be distinguishable. There are color codes that should be distinguishable. How much do you think you benefit from this implicit design decisions? And is it this probably the reason why the photographs are substantially harder for your method?
So just to understand, you ask about the detector, how it learns to distinguish the background from foreground, right?
Now, my question would be, so your work addresses cartoony characters, and cartoony characters are designed in a special way. Mm-hmm. So here, for example, the red character is for the viewer very easy to distinguish from other characters. So do you think your method benefits a lot from this, and this is one of the reasons why you get such high scores? And on the other hand, where this kind of like rule is violated, you struggle? So I believe that the fact that foreground characters are more substantial in the frame, this creator bias helps the detector to fit the boxes better, but those are learned implicitly by the labeling that we've asked our Turkers to provide. And the detector is actually not part of the main method we suggest here. Like YOLO v2 is not the state of the art. I think you have YOLO v5 now, but that's not the reason we kind of picked it, because we think that the method itself relates with the fact that we kind of suggesting a new way to estimate or to sample those triplets and fine-tune the network with respect to this hypothesis of having the characters in the same frame versus another from the tracklet. Therefore, I can show you some example from the data that we used here, which was high variance of styles, like Blender videos and public domain videos, which are far older, and Superman and Looney Tunes and other public available videos, which essentially, if having bias, then that's okay. We aim for animation, which is quite large as its own. So having some substantial characters which we can rely on, that's fair enough. Animation is quite a large domain as is.
Cool. Yeah, so thanks a lot for the great talk. Let's thank the speaker again, please.
Thank you.
Can you hear us?
Hey, hello. Can you hear me?
We can hear you, but your video, I think, looks frozen.
Oh, okay. So, can you play the pre-recorded videos?
Okay, then we can go.
Please. Oh, okay. Thank you.
Hello, everyone. My name is Weiyu from Shandong University. Today, I'm pleased to present our work, MoCo-Flow, neural motion consistent flow for dynamic humans in stationary monocular cameras. This is a joint work with Xuelin Chen, Daniel Cohen-Or, Niloy Mitra, and Baoquan Chen. Synthesizing novel views of human performance has a variety of 3D applications, such as virtual conferencing, telepresence, and so on, which can bring highly immersive experience to people's work or entertainments. Most of the previous methods rely on multi-view videos, which typically require static scenes, controlled environments, or specialized capture hardware with expensive studio setups. However, stationary monocular videos are easy to capture by only using a tripod, which means it has a significant scope and applicable in our daily life, like YouTube or TikTok. Our goal is to turn the idea into reality by using a single stationary camera that can be easily set up. You will be able to pause or rotate around the performer from any angle at any time. Let's start with some related works about human performance capture. Human pose and shape estimation mainly focus on understanding behavior, producing only coarse geometry, for example, simple template. In single-view human reconstruction, to constrain the solution space for the unobserved body parts, some model-based methods try to obtain the final geometry by deforming pre-scanned or parametric templates, usually leading to poor rendering quality due to the use of explicit geometry repetition. Others try to utilize the prior knowledge learned across a large amount of annotated data, which apparently implies the auto-distribution
Can you hear
issue
me?
when applied in the real application scenario. Recently, dynamic nerves have shown impressive performance in view synthesis. Departing from the static nerve setup, the most natural extension is to still use dense view cameras to acquire sufficient and accurate observation of the dynamic scene. Another line of extensions exploit a single free viewpoint camera from varying viewpoints, which inevitably rely on movable cameras and accurate camera extrinsics for constraining the modeling. The nerve requires the capture device to be empowered with certain mobility to allow capturing dynamic scenes. NSFF leverages external supervision such as rough monocular depth estimation and flow estimation, which unfortunately are not further jointly optimized during the optimization to resolve ambiguities. Neurobody relies on multi-view to obtain accurate pose estimation for modeling. The fewer number of cameras or more easier setup we have, the less observation we could utilize to constrain the dynamic human body. The problem of modeling a dynamic scene from a stationary monocular camera is significantly more under-constrained and ill-posed. A naive approach cannot deal with this overly ambiguous single fixed viewpoint setting. In general, to model a dynamic scene for view synthesis, it can be decomposed into a shared canonic static scene for presenting the appearance and the geometry of the subjects, and a motion flow that models the dynamics from the observation space to the canonic space at each frame. Specifically, a nerve can be used to present the static scene paired with a backward motion flow network. Both repetitions can be optimized to reproduce the observed frames via differentiable volume rendering. As is overly under-constrained problem, the lack of observation will lead to undesired local minima if we use this naive approach. The network update is prone to an erroneous overfit, as multiple solutions comprised of meaningless canonical representation and MoCo-flows can be combined together to reproduce the observation. Here, the local minima particularly refers to human bodies and dynamics that don't faithfully follow the human perception of the video. The key features of our approach in solving the above problem is to harness the challenging optimization, which including using domain-specific data priors to preset a pitfall for the optimization at the beginning, and easy-to-implement novel motion consensus regularization that prevents the optimization from climbing out the preset local minima. We exploit the simple mesh per frame extracted by the vibe as a prior, which can serve as a good initial guess for the optimization, but apparently contains errors regarding the geometry, location, and motion. See the simple estimation on the right. We then initialize canonic space using the plane mesh estimated at the canonic frame. This is done by training the canonic nerve to overfit the rough geometry and plane appearance. Without the noise of generality, we set the canonical space to be the one at the first frame. Next, we initialize the backward motion flow using the flow derived from the mesh sequence, while freezing the canonic nerve. In addition to the dedicated initialization, we have to prevent the backward motion flow from climbing out and the falling into undesired local minima. To this end, we add an auxiliary forward motion flow, which is initialized following the same pipeline as the backward flow, and we apply a local motion self-consensus regularization, enforcing the motion flow to be invertible locally between the time step Ti and the canonics. Furthermore, to achieve high consensus through the whole video, we add a global all-to-all motion consensus regularization between Ti and a randomly selected Tj, with a canonical as a transit hub. Please note that in contrast to heuristic regularization terms, a regularization on the motion flow is general and do not assume any dynamic characteristics on the moving subjects. In addition, we also include other terms for regularizing the optimization. Inspired by Nerface, we also employ a coarse-to-fine annealing strategy to gradually optimize the neural dynamic scene from modeling low-frequency details to high-frequency details. This is done by gradually increasing the number of frequency bands of the positional encoding. Since the moving subjects typically occupy a small portion of the large space, we set an adaptive bounding volume for bounding the remarching using an axis-aligned bounding box from the estimated mesh. Finally, we jointly optimize the canonical nerve and our motion flow networks using the photometric loss and the motion regularization terms. We extensively evaluate our methods on several datasets that contain human motions of varying complexity. Our method can synthesize novel views with high-quality imagery even with highly complicated motion dynamics, only using input from stationary monocular cameras. Next, we show side-by-side visual comparison to raw web outputs, showing the improvements on both geometry and the appearance of the optimization. Please note the string bind on the man's right wrist. We visualize the dense correspondence derived from the backward motion flow between the canonic body and the body reconstructed at the observation frame. We also create qualitative and quantitative comparisons against server baseline methods. Some methods failed on the task and output blank imagery. Others cannot guarantee the geometric structure of the human body and produce many artifacts. Although PSNR and LPIPS are commonly metrics in related works, they are, however, very unsuitable for our task due to the misalignment between the ground truth images and synthesized views. So we propose to calculate the plausibility and pose accuracy of the synthesized images as human imagery. We conduct experiments to compare against several variants of our method for evaluating the contribution of each component. Without the dedicated initialization step, the optimization completely failed, producing meaningless blank novel view imagery. Global and local motion consensus regularization help to preserve the geometry intact and continuous. With the absence of the adaptive bounding volume, we observe plenty of noisy artifacts in novel views. Without course to fine regularization, the optimization is very unstable and lead to noisy imagery. Thus, to conclude, we have presented a novel dynamic nerve technique for synthesizing novel views of dynamic humans from stationary monocular cameras. There are nevertheless limitations to our method in its current form. As with any monocular method, the physical factors are overly ambiguous. Thus, we cannot guarantee the correctness of physical models, and our model relies on the nerd priors for providing good initialization guess. It would also be an interesting direction to explore how the proposed method can be extended to general objects if given proper priors. Nevertheless, with the rapid advances in learning human priors, we believe that the above issues will be alleviated by stronger priors. That's all my presentation today. Thanks for your time and attention.
Thanks a lot. I think we have time for questions. Let me maybe start with one question. So I'm curious, so how stable is it with respect to very fast motions? Do you see any issues there in the learning process?
For very fast motions, for example, it's typically based on the Y post-estimation results. If you move too fast, the Y estimation is not so accurate. So for very fast motions, we can't build our motion very well.
I have actually one more question in this regard. So how many frames do you have approximately for each sequence?
For each sequence, we have about 200 frames per video. And because if we have longer videos, the time consuming is very time consuming for us. Because we have to optimize the whole video using the regular term.
Thank you. Any other questions?
Okay.
I have one more question maybe. So in terms of the,
Okay.
I'm trying a bit the scalability. So in terms of the complexity of motion, what's the relationship to the network capacity? Like basically how big do the networks have to be versus how complicated of motions can you support?
In our framework or motion network, for example, the backward flow or the forward flow network are the same as are the same structure of the nerve network. It has about 6 or 8 MLP layers, and we don't concentrate on the network structure. And we find that it's enough for us to encode the about 200 frames videos.
Okay, but how do you think this relates to the complexity, right? If you have basically more complicated motions with, let's say, like more complicated cloth, you have like wrinkles on the cloth and stuff like this. Do you think you need larger networks for that, or do you think the capacity, generally speaking, is not really an issue?
In my opinion, I think the backward or the forward network are not the issue, because I think let me think about it. I'm not sure, because we don't concentrate or focus on the network structure. Yeah.
Thank you. Any other questions? Question here.
I'm not sure I missed the information. For the training video, do you need a green screen, or is how about background requirement and the lighting conditions?
For the background, we assume the background is static, so we have matting to pre-process the whole video. Or for example, we use the mask RCN to get a coarse mask to extract the humor from the foreground to the background. That's all.
Thanks.
So we don't.
No, go ahead. Sorry.
So we don't need a green background. For example, you can see the data set. For example, let me share my screen. In dataset, we use AIST and ZGU mocap, which have static background rather than green background. Yes.
Cool, thanks. Any other questions? Okay, then let's thank the speaker again. Thanks a lot.
Thank you very much.
And with that, I'm happy to close the session.
It's my pleasure. Thank you.